Okay, hello everyone. So today we will discuss what is functionally complete operations. So today we will discuss that what are the Boolean operations that can be called as functionally complete. So from firstly we will define what is functionally complete operations, then we will proceed. So according to the definition, a set of operation is said to be functionally complete or universal if and only if every switching function can be expressed using the operations from the set. In that case, we will call the set of operations as functionally complete. Okay. Also, we know that every switching function can be expressed in canonical SOP form with the help of and, or, and not operation. So we can say that plus, dot, and negation. These three operations are clearly functionally complete because every Boolean function can be realized using these three operations. So clearly this set is an example of functionally complete set. Okay. Also, if we can uh, we can see that by using De Morgan's law, or operation can be realized using and not. How? X dash y dash whole dash will give like this expression. So or operation can be realized using and operation. So this is the logic diagram how or operation can be realized using and operation. If we apply the complement of these two variables, so and will give x dash y dash, and then if again if we take complement of this, so we will get x plus y. So in this way or operation can be realized using and not. So we can say that dot together with complement is also the functionally complete set of operation. Similarly, AND operation can also be realized using OR and NOT gate. Likewise, this using De Morgan's theorem. So we can also say that the set plus and complement or negation is also the functionally complete set. So generally what we can do, that we can remember that these two sets and together with complement or together with complement, these two sets are functionally complete set of operation. Okay. So basically there are many functionally complete set of operation exist in the literature. So how we can prove the completeness of an operation or a set of operation. So how we can prove the completeness of any operation or set of operation, and we can say that this set of operations or operation is functionally complete. So what we can do for in order to prove this thing, basically we will show that the operation whatever given is capable of generating each operation of a set that is already known to be functionally complete. Okay, so with the help of example, we will understand this thing. But basically what we have to do in order to prove that any operation is functionally complete, so what we will do, we will generate each operation of a set that is already functionally complete, that we know that that is already functionally complete. So we know that these two sets or together with complement or and together with complement, these two sets are functionally complete. So uh, so we, what we can do, if any operation or set of operation is given, we will try to generate operations from these sets. Okay okay so uh, uh, in this example, what we are doing, we have to show that NAND operation is functionally complete. We already know that f of x comma y equal to xy dash. This is the definition of NAND operation. Okay, so x y dash, which can be further written as x dash plus y dash. So if suppose we have to prove that this operation is functionally complete, so what we will do? So what we will do, we will try to generate the operations of a com, of a functionally complete set. Okay, so uh, if this is the, if this is your Boolean operation, so what we can do, we can try to generate not operation, and then we will try to convert to generate and or operation. Okay, so firstly we will try to generate or not operation. How we can generate not operation? With the help of NAND operation. So if we put y equal to x, so what will be the f of x equal to x dot complement, so which is basically x complement. So this is the logic circuit diagram. If we have given NAND operation, if we apply both input as same, so we will get x dot x complement, so which is nothing but x complement. So in this way we are capable of realizing not operation. Now we will try to realize either or operation or and operation. Why? Because not has been already realized. Now we will try to realize or and, any one of them. So so that we can conclude that NAND operation is the functionally complete operation. So we can easily see that if we calculate f of x dash y dash, so what we will get x dash y dash whole dash, which is x plus y. So in this way OR operation can be easily realized. How? We have already realized complement. So here we can get the complement of any input, and then we can get the complement of another input, and then these two complements are again applied to the NAND operation. So in this way we will calculate f of x dash and y dash. X dash and y dash are already realized. We can easily realize x dash, so it will give x dash y dash whole dash, which is x plus y. Okay, so in this way we can realize the OR operation. So here we can conclude that NAND operation is functionally complete because it is able to provide not operation. It is also able to provide or operation. Also we can derive the expression for the AND operation. Also we can derive the expression for the AND operation using NAND operation. So basically fxy is given like this. If we take the complement of this function xy dash whole dash, then it will give the xy. So uh, in this way we can also realize the AND operation also. So x and y are applied and then NAND operation is taken, that will give the complement. From the complement, how we will get again the same function? So we will make this both input as same and then it will give xy. Okay, here also we can see that from how we can get the complement, we will make both input as same. In this way we can get the complement. So we can conclude that NAND operation is functionally complete. Okay. So again in this example we have to show that NOR operation is functionally complete. So how we will do in order to prove that NOR operation is functionally complete? What we have to do? We will take the definition of NOR operation and we will try to generate any known functionally complete set of operation using this operation. Okay, so either we have to generate OR and complement, or we can generate or and complement operation. So firstly, do remember, firstly we have to realize the NOT operation. Okay, so how we can realize the NOT operation? Simply put, make both the variable as same. So it will give f of xx equal to x plus x dash, which is x dash. This is the logic circuit diagram. If we make both input as same, that will give the complement. Okay, so NOT operation can be easily realized. Okay, so again, if we make both, if we apply the complements of both the inputs, so f of x dash comma y dash, what it will be? X dash plus y dash whole dash, based on the definition, which is nothing but xy. So we will take the complement of each input and then again apply it to the NOR operation. It will give xy. So with the, with this point we can conclude that NOR operation is functionally complete. Okay, still if you want to realize OR operation, we can also realize fxy is x plus y dash. Somehow we have to obtain the x plus y. So what we will do, we will take the complement of this operation, f dash x comma y, okay, equal to x plus y dash whole dash, which is x plus y. So we will take two inputs and we have applied to NOR operation, it will give this. And if we apply both inputs to the NOR operation, then it will complement this expression. So it will give x plus y. Likewise we have done here. Okay, so basically what we are doing, if we want to prove any operation or set of operation to be functionally complete, then what we have to do, we will try to generate a set of functionally complete operation which is already known to be functionally complete, and then we will try to derive the operations in the functionally complete set using the given operation. Okay, so basically what will be the general strategy? So general procedure to prove that any operation or set of operation is functionally complete. Firstly, what we will do, we will write the given operation if only one operation is given, or set of operation in SOP expression. Okay, and secondly what we will do in second step, if there is no complement in any of the expression, then NOT cannot be realized. If we are not able to realize NOT operation, then we can simply conclude that this set of operation or operation is not functionally complete. So we will return from here. Okay, so in the first step we will write the SOP expression for the operation, for the given operation, and then we will try to realize the not operation. How we will drive, how we will try to realize the not operation? Generally what we will do, we will equate, we will try to equate all the variables, and then we will try to realize not operation. If there is if there is nowhere complement appears in the expression, then it is not possible to realize the not operation. Do remember, we can return from here by stating that this operation is functionally incomplete. Okay, in the third step, what we will do, if a complement appears in any one of the expression for the given operation, then not may be realized by appropriate choice of inputs. Okay, so generally we will try to select inputs in such a way that if so that we can realize the not operation. So do remember, if there is no complement in any of the expression, then we can simply conclude that not cannot be realized. If complement is present, then we will choose appropriate choice of input so that not can be realized. Okay, so firstly we will try to realize the not gate. If not gate is realized, then we will try to realize either and or. Okay, by remembering that not is now available. Okay, if any one of them is realized, so we can say that we have realized not operation and operation. So this set of operation is already functionally complete. So we can say that the given expression is functionally complete. Or we have realized not operation, and we will try to realize or operation. We already know that this set is also functionally complete. So the given operation or set of operation is said to be functionally complete. So basically to this is the general procedure to determine whether a given operation or set of operation is functionally complete or not. We have already seen that NAND operation and NOR operation are functionally complete. Now if you are given some if you are given any operation, then we will try to realize not operation and AND operation by using that operation, or we will try to realize these two operations. Okay, firstly we will try to realize not. Okay, do remember. So this is the general procedure. Okay, so now we will look into few examples of functionally complete operation. Okay, so in this example we have to identify whether this operation is functionally complete or not. So what we can do, we already know that not together with AND is functionally complete, and we also know that not together with OR is also functionally complete. So from the given operation we will try to generate either these two operation or these two operation, and then we can conclude that this operation is functionally complete. So whenever we will try to generate any known functionally complete set of operation, then firstly we will try to generate not operation. In order to generate not operation, we generally do, we will make all the variables as one variable. So if we calculate f of x, what will be the x plus x x dash. So x dash is nothing but 0. So we are easily derive x dash. If we make all three inputs as same, then we will easily get the x dash, complement of a variable. So in this way not operation is realized. After realizing the not operation, what we will do, we will try to realize either and or or. Okay, so here we are given the operation in SOP form. So firstly we will try to generate OR operation. Okay, so it is the x dash plus y z dash. It is the given operation f of x y z. Okay, so we have to generate OR operation, which is OR operation is nothing but x plus y. Okay, for two variables. So here what we can do, if somehow I can manage x dash to be x and z dash to be y, then we can easily get x plus y into y, which is x plus y. So in this way we can obtain the OR operation. So what we are needing, somehow we have to generate x dash to x. So how we can get the x from x dash? Simply uh, if uh, if I put x dash dash, we can get the x. Okay, and similarly uh, how we can get y in place of z dash? How? If in place of z we put y dash, of dash will always give y. So what we will do, so f of x y z is given x dash plus y z dash. So in place of x, somehow I have to obtain the complement. So we can write like this: f of x comma x comma x, which is nothing but x dash, and then in place of y we need y. In place of z, what we have to obtain? Y dash. Okay, so we will calculate f of y, y and y. Okay, so f of x, x is nothing but x dash. Similarly, this is nothing but y dash. Now, uh, we can proceed further like this. Uh, f of x y z is basically x dash plus y z dash. So we will open this function as like this, equal to x dash dash plus y z dash, we are placing y dash dash, so which is x plus y into y, which is x plus y. So in this way we can realize the OR operation. So we can conclude that the given operation is functionally complete. Okay, so what we have done, using given a operation we have realized the not operation. How we have realized the not operation? We have made all three variables as same, similar to what we have done in NAND and NOR operation. So here we have made all three variables as same, so we will get the x dash. In this way we are easily able to derive not operation. After realizing not operation, we will try to realize and or operation. So This is the given definition x dash plus y z dash. Somehow it is clear that it is easy to derive OR operation. We we are trying to realize the OR operation. Okay, so how we can realize the OR operation from by looking into this expression. If we somehow obtain x in place of x dash and in place of z dash we can if somehow we manage y, then we can get x plus y easily. Okay, we can get x plus y, so we have to make x dash as x. So how we can do? If we place x by x dash, then we can get the x. Similarly, if we place z as y dash, we can get the y in place of z dash. So this is the given expression. Okay, so in place of uh, x we need x dash. That's why we are using definition of nested function. So in place of x we are putting f of x, which is nothing but x dash, because we have seen that x how not is derived. So here we will get x dash, and this is also y dash. Now we will open with with the original definition. So in place of x we will get x dash whole dash plus y. In place of z we will get y dash, because we have used nested function. So in this way we will able to derive OR operation. Okay, now we will look into another example. Okay, so in this example, we have given this operation. Now we have to find out whether this operation is functionally complete or not. So obviously we will try to derive NOT operation with AND operation, NOT together with OR operation, or we will try to generate NOT operation together with AND operation. Okay, so initially we will try to generate NOT operation. So in order to generate NOT operation, what we can generally do, we will make all the variables as same. So f of xx is x dash plus x. Okay, so it will always be 0. Okay, now we will try to make y as x as y. So f of y, in place of x we have written y. So y dash plus y, again it is giving 0. So clearly we are not able to derive complement here by using this operation. So another thing is that we can take either 0 together with function. We can take either 0 and 1 as input in order to generate the some other functionally complete operation. Okay, so if somehow if we add if somehow if we make y as 0, so we can easily get the x dash. So f of x comma 0, what will be x dash plus 0, which is x dash. Okay, so in this way we can get the complement. So do remember, we can, other than the operation, we can also take 0 and 1 as input. If we are taking 0 and 1 as together with the given operation, in that case if we uh, conclude that the given operation is functionally complete, then what we can say, this operation is partially functionally complete. Okay, so if we are using 0 and if we are using only the operation, and we are somehow able to show that this operation is functionally complete, so we will say that this is functionally complete, fc. Okay, if we are using f together with 0 or 1 as input, In this case, if we are able to show that this operation is functionally complete, in this case we will say partially functionally complete. Okay, if uh, if we are not able to generate uh, if we are not able to generate functionally complete set, then clearly we will say that it is not functionally complete. Okay, so generally what we can say, if we are using only the operation without the help of 0 and 1, in this case uh, either the function will be functionally complete or partially functionally complete. Okay, so in this operation we are taking the help of 0, so clearly we are able to drive not operation. Okay, now we will try to drive either or not operation. Okay, so clearly here uh, it is easy to drive or operation. So what we can do, in place of x dash somehow we need x, so it is easy. How? F of x comma 0 will give x dash, and then we are taking y. Okay, so it will give x dash dash plus y, which is x plus y. So this set of operation is clearly functionally complete. Now we will look into another example. Okay, so in this example, the definition of operation is given. Now we have to look whether this operation is functionally complete or not. So simply we will try to generate not operation and then either of or and operation. Okay, so we will try to generate not operation. So for not operation, what we can do, we will make all the variables as one variable. So f of xx is x dash x. X dash x is will always give 0. Similarly, if we make x as y, then f of y is y dash y, which will always give 0. So here also we are not able to generate complement. So what we can do, we can take 0 or 1 as input. So here if we make y as 1, so we can easily get the x complement. So f of x comma 1 is x dash 1, which is x dash. So clearly we are able to generate not operation. So now we will try to generate either and or operation. So here from the expression it is clear that it is easy to generate and operation. So for generating and operation, we have to somehow make x dash as x. How we can do this? How we can make x dash as x? If we somehow make x as x dash. Okay, so we will try to calculate f of uh, x comma 1 and then y. It will x dash dash into y, which is xy. So clearly we are able to generate AND operation here also. So this operation is functionally complete. Do remember. Okay, so now we will look into another example. Okay, so in this example, the definition of operation is given like this. Okay, so now we have to check whether this operation is functionally complete or not. So from the procedure whatever we have written, we know that firstly we will try to realize not operation, and then we will try to realize either or and operation. Okay, so also we know that if the operation does not have any complement, any literal in complement form, then it is not possible to generate not operation. So here nothing is in complement form. In this function nothing is in complement form, so it is impossible to generate the not operation. If we are not able to generate not operation, then uh, then we can simply say that this operation is not functionally complete. So clearly from here we can conclude that this function or operation is not functionally complete. Okay, so now we will look into another example. Okay, so this is the given function fx comma y equal to x dash y plus x y dash. So this is nothing but exclusive or function. Okay, so now we have to check whether this operation is functionally complete or not. So similar to the our procedure, we will try to generate not and then any one of and or operation. Okay, so in order to generate not operation, what we will calculate f of x comma x. It will give x dash x plus x dash x dash. So this is 0 plus 0, which is 0. Okay, so now we will try f of y comma y, x y dash y plus y dash, which is again 0 plus 0, so 0. So clearly we are not able to generate not operation here. So now we will take help of 0 or 1. So we will try to generate not operation with the help of 0 and 1. So if we make y as 1, so we will get here x dash. Okay, so y1, so it will be 0. So if we calculate f of x comma 1, here we are making y as 1, so what we will get, x dash 1 plus x 0, it will 0. So clearly we are able to get x dash. So here with the help of 0 and 1 we are able to realize not operation. After realizing not operation, possibly we can conclude that whether it is functionally complete or not, functionally complete or not, if it is able to realize and or operation. Okay, so it may be partially functionally complete. Okay, so now we will try to generate either or operation and operation. So if we try to generate or operation, so what we can do, we can make f x comma y dash. Firstly we are making y as y dash, so what we will get, x dash y dash plus x y. Clearly it is not neither the or operation nor not the or and operation. Okay, now if we calculate f of x dash comma y, what we will get, we are placing x dash in place of x, so x y plus x dash y dash, again we are getting the same function. So we are uh, another option, if we calculate f of x dash and y dash, if we make both variable as complement, then what we will get, x y dash plus x dash y. Okay, which is the same given function. So we have tried all the possibilities. We are placing generally y. We are making second variable is complement, first variable is complement, both is complement, still we are not able to generate x plus y. So another options are, if we make both the variables as same x and x dash, just suppose, but in this case we will not get the two variables, so this case is clearly ruled out. We should not use this or like x dash or x, because both of these will give only the function of x. Okay, so we should not try these. Similarly, we should also not try y dash and f of y dash or y. Again, these two variables will provide, these two will give the functions of y. Okay, so clearly we are not able to generate OR operation here. So this function exclusive OR is clearly functionally incomplete. We cannot generate all the Boolean function using exclusive OR. Do remember. Similarly, you can also prove that f of x comma y equal to xy plus x dash y dash. This function will able to generate not operation, but will not be able to generate or or AND operation. Okay, so this operation is also functionally incomplete. Okay, so this is all about functionally complete set. So in this way we can do and proceed for any given operation or set of operation. Thank you.